Hello, today we're continuing with our series on GCSE physics revision, and we're going to be looking at magnetic fields and motors. Here is an ordinary bar magnet, and it will have a north pole and a south pole. Magnets are not unlike charges, and in particular a magnetic pole is not unlike a magnetic charge, as we shall see. But there is one critical difference. If you consider an electron, which we've looked at earlier in this series, an electron has a negative charge and it is a standalone entity. It's negatively charged, it's an electron. But when you have a magnet, you always have a north pole, you always have a south pole. You can never have a north pole on its own. That would be called a monopole, and they don't exist. Wherever there's a north pole, there's a south pole. The Earth is a magnet. It has a north pole and it has a south pole. And from the magnet you get a magnetic field. And the magnetic field goes from the north pole to the south pole. So round the Earth there is a magnetic field. And the direction is north to south. The value of that magnetic field, its strength, is represented in equations by the letter B. So whenever you see B, you know that represents the magnetic field. Now, do you remember this statement? Like charges repel, unlike charges attract. We stated that in an earlier video about the way in which charges interact. You can replace charges with the word poles and then you get like poles repel, unlike poles attract. So what we're saying now is that if you bring two north poles together, or indeed two south poles, they are like poles, they will repel because their fields are pushing away from one another, and that creates a force that will cause those two poles to push apart. If you try and bring two north poles of a magnet together, you'll find it very difficult to do so. They will try to slide to one side. They will not be pushed together. By contrast, if you bring a north pole and a south pole together, that's fine because the field lines go from north to south, and there will be an attraction. They will want to get at one another, so the force will be an attractive force. So like poles repel, unlike poles attract. Now this is where we learn that electricity and magnetism are related. If you take a current in a wire, so here's a wire, I won't draw the rest of the circuit, but obviously there has to be a circuit to derive the current, which has a value I, then around that wire there will be a magnetic field. And I've got to draw this these are concentric circles, but essentially they are going into and out of the page because the wire is going up the page and the concentric circles are around the wire. And there will be a field. The arrows indicate the direction of the field. And to work out which way the field will be moving, you use this kind of right-hand corkscrew rule. What you do is you take your hand and you curl your fingers and you let your thumb point out, and it's your right hand. So let the thumb be the direction of the current, so that's pointing upwards, and you'll notice that your fingers are curling in this direction, and the way they curl is the direction of the magnetic field, and you'll notice they curl clockwise according to the current. So if the current is going up, the field will go clockwise around the cable. So a reminder, the current is going that way, that's the direction of the thumb. The fingers are going round this way, so that is going to be the direction of the magnetic field. Suppose I now organise my wire like this, such that I've got my current flowing like that. The current will flow along the top and down this side of the wire. So on this side the current is flowing in that direction. What about the magnetic field lines now? Well, first we'll consider the right-hand side of the wire where the current is going up. So my thumb points up and my fingers are curling round in this way. Since the wire is going up, the field is essentially going into and out of the paper. On this side, it's coming out of the paper because my fingers are pointing up. So the way we show that is that we put a dot. That's rather like looking at an arrow. The arrow would be coming towards you and you would see the point of the arrow. On this side, the field lines are going into the paper, which we represent like this. That's like you're seeing the tail of the arrow disappear from you. So thumb says that the current is going upwards. The field lines on this side are coming out of the paper. That we represent with the dot, coming out towards us. On this side, they're going into the paper. Now let's think about this side of the equation. This time, the thumb has got to be pointing downwards. So I point my thumb in that direction. And now, on this side of the paper, the field lines are going into the paper. So on this side, they're going into the paper, which remember was the arrow going away from you. And so obviously, pretty clearly on this side of the paper, it's going to be coming towards you. Now, look what's happening between the two wires. The field is the same inside. In other words, in both cases, the field is coming towards you. The field is reinforced within the two wires. So suppose I have several coils of wire. And I send a current through here. That's going to travel through like that. When it gets up to here, it's going like that. When it gets down to here, it's going like that. When it gets up to here, it's going like that. It's just continuing its journey. But you can see at the top of the wire, the current is going in one direction. At the bottom of the wire, it's going in the other direction. This, don't forget, is a coil that's essentially coming out of the page. You can't draw it terribly well. But if I were to look at it, if I were to kind of slice that in half, you would effectively have cables coming in and out of the page. And we can represent whether it's coming in or going out, in other words, whether the current is coming in or out, by dots and crosses. What we say is if you look at an arrow, if it's coming towards you, coming out of the paper, that's a dot. If it's going into the paper, that's a cross. So let's suppose that at the top, this is coming out of the paper, this is going into the paper. So if it's coming out of the paper at the top, we put dots because an arrow coming towards you, you just see the dot. Whereas if it's going into the paper, we put a cross because an arrow going away from you, you see the tail feathers that look like that. So essentially the current is coming out of the paper, going into the paper, coming out of the paper, going into the paper, coming out of the paper, going into the paper, coming out of the paper, going into the paper. Which way does the magnetic field work? Well, let's just think about the top line where the current is always coming out of the paper in the wire. I now need to put my thumb in the direction of the current, which is out of the paper, so it's pointing towards the camera. And you can see that the field goes round in this direction. Around each wire, it will be travelling like that. What about when the field is going down into the paper? I have to contort myself now. The thumb is now pointing downwards and consequently my fingers are pointing round in a clockwise direction. So that's like that, like that, like that, and like that. And now you can see what's happening. This field here is going in a clockwise direction here, but an anti-clockwise direction here. The field here inside is going to the right. The field here inside is going to the right. We've got a constant field. And of course, it goes from north to south. So this is a north-south arrangement. If you put a piece of soft iron core in the middle of the coil of wire, that will enhance the strength of this magnetic field. And when you do that, that is called an electromagnet. And you'll notice that the magnetism only arises when the current is flowing. So if you switch the current off, the magnetism goes. So this is rather like a bar magnet. Outside the bar, the field lines are rather like a bar magnet. Inside the coil, you've got a strong and consistent magnetic field. And that strength can also be increased by having more turns per length. So if you have, say, 5 turns per centimetre, that will give you a certain field strength. If you have 10 turns per centimetre, you'll get an even larger field strength. The coil of wire is called a solenoid. When you put the iron core in the middle to enhance the magnetic field, that becomes an electromagnet. And a key virtue of an electromagnet is it's only magnetic when the current is flowing. Switch the current off and there's no magnetic field. Now I want to consider the situation whereby we have a magnet, and the magnet might be shaped something like this. This is a kind of almost horseshoe type magnet where you have a north pole and a south pole. And all I'm going to be looking at is this bit of the magnet here. In other words, there's a gap between the two. So here is the north pole, here is the south pole of that magnet. I'm not going to bother with the rest of it. And I've got a wire which is effectively going into the paper. So it's essentially coming up out of the paper, and my current is going to flow into the paper. So if the current is flowing into the paper, we represent it as a cross. That means that the current is going away from me into the paper. The wire is going into the paper like this. Pull this down a little. The field lines, of course, go round. If I've got the current going down, I use my thumb pointing down, and the fingers curl round clockwise, so the field around the current is going round in this direction. But there is also, of course, a field between the north and south poles of the magnet here. So I've now got two magnetic fields. A magnetic field that is going round the current in the wire that's going into the paper, and a field that's going from north to south in the magnet itself. And we've just learned that magnetic fields interact. North poles will repel, in other words, like poles repel, unlike poles attract. So there's going to be some kind of force that's going to be is going to arise because of the interaction of these two fields. And what you find is that the force is acting in a direction that is both perpendicular to the magnetic field and perpendicular to the direction of the current. Well, the magnetic field is going, as it were, from right to left. The current is going from out to in, and so the force will be either up or down. How can you tell which direction the force will be? Well, now you have to use your hand again, but this time it's the left hand. When we were working out which direction the current goes round, the magnetic field goes round a current, we used the right hand corkscrew rule. Now we're going to use what's called Fleming's left hand rule. And you have to organise your fingers like this. You want your thumb, your first finger and your second finger. The other two you can forget about. And you have to arrange them like this, so that they are effectively perpendicular to one another. My thumb is sticking up out of the paper, my first finger is pointing up, my second finger is pointing that way. So I've got, as it were, 3 dimensions of fingers here. Now, my thumb stands for the motion, the direction in which the wire will move. My first finger stands for the field, the direction of the magnetic field from north to south. And my second finger stands for current, the direction of the current. So my field is pointing from right to left. So I need to point my first finger from right to left. So I need to contort myself for this. So here is my first finger pointing in the direction of the field, north to south. My second finger, my second finger has to be the current. The current is going into the paper, so I point my second finger down, and that means my thumb is going to point in the direction of motion, which is upwards. So the wire is going to move upwards. And that's because there is a force, an electromagnetic force, which arises because of the interaction between the field of the magnet and the field around the current in the wire. The strength of that force is going to be proportional to the current in the wire. So the stronger the current, the greater the force. And the force is also going to be proportional to the strength of the magnetic field between the north and south pole of the magnet. But let me just remind you again that the magnetic field, the current and the force act perpendicular to one another, which is why you need to have your fingers arranged in this way. The motion is the thumb, the field of the magnet is the first finger, and the direction of the current is the second finger. So here's a typical exam question. Here is my magnet, it's north-south. So the field is obviously going to go from left to right. I've got a wire that is going in this direction, and the current in particular is going downwards. In those circumstances, the force on the wire must be in the third dimension. I've got left, right for the field. I've got down for the current. So the force is either going to be into or out of the paper. Which way will it be? Well, first of all, I need to put my first finger in the direction of the field. That's pointing from north to south. My second finger needs to go in the direction of the current, which is down. So I've got first finger pointing in the direction of the field, second finger in the direction of the current, which means my thumb, which is pointing up at you, pointing out of the paper, must be the direction of the motion of the wire. So consequently, the direction of the wire will be out of the paper. Now let me set up an arrangement like this. I'm going to have to draw something that looks as though it's three-dimensional, but on a two-dimensional sheet. So that's a bit of a challenge, but we'll rise to it. So here we have a magnet. This is the north and this is the south. And I have a coil of wire, which in a sense is going into the paper. And I send a current through that wire such that it goes like this. Obviously the current travels round the wire, so on this side it's travelling into the paper, on this side it's travelling out of the paper. Where I have a current in a wire in the presence of a magnetic field, there will be a force on the wire. We've just established that. Let's take this side of the wire and find out which way the force will act. Once again, we're using the left-hand rule. It's called Fleming's left-hand rule. We want the first finger in the direction of the field, north to south. Second finger in the direction of the current, that is going downwards. So the motion of the wire will be upwards. My thumb was pointing up out of the paper. So the coil is going to go up, or rather that particular bit of the wire is going to go up. What is going to happen on that side? Well, the field stays the same, but the current is now in the other direction, which means the motion of that side of the wire will be down. If I put this whole thing on a spindle or an axis, rather like putting a meat skewer through it, what's going to happen is that it's just going to twist. This side will come up, this side will go down, and the thing will turn completely over. So it's like my hand will turn like this. This side comes up, this side goes down, it turns like that. That's exactly what will happen. But it'll only get halfway round, because when it gets halfway round, this side of the wire will now be on this side, but the current will still be going in this direction. And when the current is going in this direction, when it's coming downwards, then the force will be upwards. And similarly, this wire, when it gets to this side, will still have a current going in that direction. So now instead of the force being up, the force will be down. So all that will happen is that this will just flip. First it will go like that, and then it will go like that. So it just flips back and forth, which is okay, but it's not much use. So what you do is you arrange for these wires to be connected to what are called split ring commutators. And those are connected to the battery. So I've got a battery connected to split ring commutators. The point being that as this spins, this cable here, which for the time being is connected to this commutator, once it spins round, will be connected to this commutator. So whichever wire happens to be on the left, it will be connected to this commutator, and the current will always flow upwards. Similarly, whichever wire is connected to this commutator will always be connected to the negative side of the battery, so the conventional current will always travel downwards. And in those circumstances, this will just continue to spin. And I could put something on the end of this, like a little fan, and I would get a spinning fan. And what I have developed here is simply an electric motor. The speed of rotation of that motor will be proportional to the current that's flowing through the wire. The more the current, the faster the speed. It will be proportional to the magnetic field. In other words, the stronger the magnet, the faster you get to turn. And it will also be proportional to the number of turns in the wire. At the moment, I've only got one turn. What I could have done, of course, is to go up, down, round, and then round again, and then bring the two wires out. That would be a two-turn wire. I could have as many turns as I like. The more turns you use, the faster the whole motor will rotate. And that's the essence of an electric motor. An electric motor produces a rotating wire which can drive anything you want to turn, like a screwdriver or an electric saw or whatever. In practice, if you look inside an electric motor, what you're most likely to find is that the magnetic field or magnetic poles are shaped in this kind of way, and then there's a big coil which spins on a spindle. The coil, of course, is connected and the current flows through the coil. That causes that coil to flip, and that will drive whatever it is you want to drive. The reason that the field, the magnet is arranged in this way is that intensifies the strength of the field between the north and south poles. So you get a larger B value, larger magnetic field value, and the larger the magnetic field value, the greater the speed. The greater the force, actually, that is applied to the wire.